In this podcast, we'll be looking at Newton's final law of motion, the third law of motion. It's probably one which a lot of students actually know, but possibly don't fully understand. It's often stated as for every action there is an equal and opposite reaction. But what does this actually mean, and how does this statement relate to forces and motion? So firstly, the word action refers to a force. So we can say for every force there's an equal and opposite reaction force. So have a look at this picture here. This picture shows two stick figures, A and B, and A is pushing on B, and as a result B pushes on A. And Newton's third law says that the two forces, the force of A pushing B, and that's the blue arrow, is equal but opposite in direction to the force of B pushing on A. So we can write the force of B pushing A is equal but opposite to the force of A pushing B, and that's why we have a negative sign in there. Now we can actually demonstrate this in a real scenario with force sensors. And if we give each of these people a force sensor and hook them together, and they pull and push at each other, and we graph the results, we can very clearly see that the two forces are equal in magnitude but opposite in direction to one another. Person A has one force meter and person B has the other. So the red line represents person A's force and the blue line represents person B's force. They're equal but opposite in direction. So Newton's law says that for each force, for every force, there's an equal and opposite force. It's important to note that these forces, this pair of forces, act on different objects. If they were to act on the same object, the resultant force would be zero. Equal and opposite forces on the same object would cancel out and we'd never have any acceleration in the world. So it should be fairly clear that they must act on different objects. Take a look at these two pictures. These are two diagrams with some forces shown, and both diagrams are correct. This diagram here shows a man standing on the earth. The red arrow is showing the weight of the man, the force of gravity on the man. The orange arrow is the reaction force from the ground pushing up on the man, which is as a result of his weight. So both of these forces are on the man. The weight is on the man, and the reaction force is pushing up on the man. So these two forces here aren't what we would call Newton's third law pair of forces, but these two are. So we still have the weight of the man, that's the force of gravity pulling on the man, and here the orange arrow represents the pull of gravity between the man and the earth. It's the pull of gravity from the man on the earth. So these two forces are equal and opposite, and the red arrow is the force on the man, and the orange arrow is the force on the earth. So these are equal and opposite and acting on different objects. So this pair of forces here we would describe as a Newton's third law pair of forces. So these equal and opposite forces experienced by the objects are going to affect the object's motions. So Newton said that if a body impinges upon another and by its force changes the motion of the other, that body also will undergo an equal change in its own motion towards the contrary part. The changes made by these actions are equal, not in the velocities, but in the motions of the bodies. So what did he mean by that? Let's have a look at a couple of scenarios. So in scenario 1, I've now put person A and person B on roller skates, so they're free to move around. Now if A and B have the same mass, what do you expect is going to happen? So A pushes on B. Newton's third law says that B is pushing on A with the same force. So they're experiencing the same force. They have the same mass. They're going to experience the same acceleration from Newton's second law, F equals ma. So they will result in having the same speed. They will move away from each other with the same speed because their masses are equal. Let's take a look at another scenario. So now person A has teamed up with a heavier person B. What happens this time? So person A is pushing on person B with a force. Newton's third law states that B must push on A with the same force. What's going to happen? So now B is going to move away from A at a slower speed because B is heavier, it has a greater mass. B will experience a smaller acceleration. Even though the forces experienced by each person are the same, the acceleration experienced by B is smaller because B's got a bigger mass. Let's take a look at how that's explained by Newton's second law. So Newton's second law, we've stated it as F equals ma. So ignoring the direction of F, just looking at the size of F, we can say that the force experienced by A is the same as the force experienced by B. Or we can simply write down, because of this expression here, mass of A times acceleration of A is equal to mass of B times acceleration of B. So if the mass of B is increased, if the mass of B is bigger, the acceleration of B must be smaller so that the equation still remains balanced. If mass of B goes up, acceleration of B must go down to maintain the equation's balance. If the mass of B was smaller, then we can see that the acceleration of B would have to be bigger to maintain the balance in the equation. This small applet hopefully explains that or shows that quite clearly. So in this first situation, we have an object sitting on an air track, which reduces the friction between the surface and the object, and it's going to move and collide with another object which has the same mass. Let's see what happens. So the first object collides with the second object, and the first object stops, and the second object starts and moves off with the same speed as the first object. So you can see that the change of speed has been the same. The first object has stopped and the second object has started, and it's actually moving off with the same speed as the first object. So their change in speed is the same, which indicates that their acceleration is actually the same as well. Now if I make the second object heavier, what's going to happen this time? Now when the second object is heavier, the second object experiences less change in speed, and the first object experiences a greater change in speed, a greater acceleration, and hence a greater change in speed. We can see, if I play that again, we can see that the first one actually bounces back, and the second one doesn't move off quite as fast. If I reduce the mass of the second one, let's see what happens this time. In this case, the first one is actually still moving in the same direction, so it's not experienced such a great change in speed. The second one, however, is moving off faster than the first one was moving. Let's just look at that one more time. So the initial speed of the cart, the left cart, is 1, and then the speed of the second car after the collision is greater than 1. Let's go back to the heavier cart. The initial speed of the cart here is 1, and then the speed after the collision of the second cart is less than 1 because it's heavier. So if a car and a truck collide, God forbid, the car will come off worse, even though they experience the same force. And this is because the car is lighter and it experiences a greater acceleration. Now I don't want to look at a car-truck collision, but we can see the same effect with a golf ball as well. So here's a golf ball getting ready to be hit by a golf club. Let's see what it looks like. Now you can see what happens there. If I rewind it a little again. When the golf club hits the ball moves away faster than the golf club. And that's because the golf ball is lighter than the golf club itself. The golf ball is lighter than the golf club. This change in speed of the golf club is very small, and we can't really see the change in speed of the golf club. But of course we can see a very great increase in speed of the golf ball. It goes from 0 to a very fast speed. The golf club doesn't really slow down very much, and the golf ball speeds up a lot. So in summary, forces always occur in pairs, equal in size but opposite in direction. The forces will be on different objects, and the effect of the forces will be different for each object and will depend on their mass.